So today we're going to talk about the different layers of the Earth, from its surface to its center. So about the interior of the Earth, it's been speculated about since ancient times, but without the ability to directly observe the Earth, given that we only experience its surface, we can't experience the interior of the Earth. And so a lot of fantastic images were developed, especially throughout literary history. Earth has been described as a fiery dungeon-like underworld. It's been described as a sponge-like space filled with water, rock, and air. And it's also been described as a series of interconnected caverns in the popular novel A Journey to the Center of the Earth. But today, the interior of the Earth is known to be characterized by distinct layers, which are shown here. And this conclusion incorporates several key lines of evidence which help to explain the Earth's layered nature, as opposed to the fiery dungeon-like underworld. But how do we know that the Earth has layers? So some of these specific lines of evidence are based on early estimates of the Earth's density, including Neville Maskelyne's plumb bob experiment in 1776. His findings show that while the density of the surface rocks is relatively minimal, the density of the overall Earth is actually a lot greater, which indicates that the interior of the Earth must have some very dense material. And this led to Emil Weichert's speculations about the metallic composition of Earth's interior, given that metals are typically dense materials. Also, the study of the tides has revealed a lot about Earth's interior, given that it must be largely solid, because if the interior of the Earth was largely liquid, then the surface of the Earth would shift much like the tides do on the surface of the sea. Also, the study of earthquakes has given us a lot of information about Earth's interior, given that seismic waves travel at different velocities through different materials, as shown in this diagram here. And the changes in these wave velocities reveal boundaries between various layers of the Earth. And finally, the principle of the geothermal gradient, in which Earth's temperature and pressure increase, as in the graph shown. That's shown us a lot about how the solid inner core of the Earth is as the result of pressure and compaction. And Earth's layers and their composition. So after we determined that the Earth was subdivided into layers, we identified them as the crust, the mantle, the upper and lower mantle, the core, which is divided into the outer and inner core. And geologists began to attempt to discover the composition of these layers by various experiments regarding the sources of magma, or studying chunks of rock that could have been carried through the Earth's interior, or examining the compositions of even meteorites that could serve as a source of knowledge that's similar to the composition of our Earth. So as a result, we have a relatively well-defined idea about the Earth's layers and their composition. So the first layer we're going to look at is the crust. And the crust is the outermost layer, and it's the layer with which we as humans are able to interact the most. The thickness of the Earth's crust was first determined by Andrea Mohorovicic in 1909 through the use of earthquake data. He observed an increase in seismic wave velocity, just tens of kilometers below the Earth's surface, suggesting a change in the properties of the rock at this depth. Thus, the boundary between Earth's crust and its mantle has been labeled the MOHO, or the Mohorovicic discontinuity, which is labeled here. In fact, the Earth's crust, depending on the Earth's location, relative to different places, can be 0.1 or 1% of Earth's entire radius. So the crust is a relatively thin portion of the Earth's layers. And you can actually compare it to a balloon, an inflated balloon. If the Earth were to be an inflated balloon, the portion represented by the crust would be equivalent to the balloon's skin. So as we know, the Earth's crust is very, very thin relative to the overall composition of the Earth. And it varies, as you can see, among continental and oceanic crust, which we're going to talk about here. So we've got two different types of crust that we can look at, oceanic crust and continental crust. And oceanic crust, as you might assume, underlies the ocean floor. It's generally about 7 to 10 kilometers thick, and it is blanketed by a layer of sediment, and then its composition is mostly basaltic, and then there's a little bit of gabbro. So overall, oceanic crust is thin but dense because of its mafic content, and continental crust is generally a little bit thicker, about 35 to 40 kilometers thick, but its thickness is more variable given plate tectonics and different convergent and divergent boundaries, creating thinner and thicker stretching and pulling of that crust. And it's also more felsic and intermediate in composition, so it's less dense than oceanic crust, but it's actually thicker, which is why oceanic crust tends to subduct at convergent boundaries with continental crust. And as you can see, the varied thickness of the continental crust atop the oceanic crust here. And overall, the crust is the most rigid layer of our Earth, and it causes it to bend and break with the movement of Earth's tectonic plates, as opposed to flowing like other layers of the Earth will do, as we'll see as we move on. So the next layer of the Earth is the mantle. And the mantle is the layer which falls directly below the crust, and it forms a 2,885 kilometer thick layer around the Earth's core. So it is very, very thick, and that means that by volume, the mantle is the largest portion of the Earth. It consists almost exclusively of ultramafic rock, and peridotite is one of the rock contents that makes up the primary composition of the mantle. And so based upon observed changes in seismic wave velocities, scientists have been able to differentiate between the upper mantle and the lower mantle, and there's a transition zone that lies between them, as is demonstrated by this diagram here. We have our lower mantle and our upper mantle, as well as our transition zone. The mantle is considered to be almost exclusively solid rock. However, mantle rock below a depth of about 100 to 150 kilometers is hot enough to flow convectively, but it flows at a rate of about 15 centimeters per year. So it's relatively slow flow, and while this rock is not liquid, the mantle is considered to be what we call plastic, and that means that it can flow very slowly without breaking, as opposed to the rigid crust, which will bend and break. So now let's review some terminology. We know that the Earth's most identifiable distinctions about its composition can be done among its layers, but the interior of the Earth can also be classified based upon its ability to flow. So we've already talked about two of the layers, but now we can review some different terms, including the lithosphere and the asthenosphere. So we can serve to distinguish between the rigid materials of the Earth, like the crust, and the plastic materials of the Earth. And so the outer layer of the Earth has been termed the lithosphere, and it's composed of the crust and the uppermost portion of the mantle, which is termed the lithospheric mantle. So the lithosphere lies atop the asthenosphere, which is the portion of the mantle rock which does in fact flow. However, we have to remember that this rock is not liquid simply because it flows. It's actually just plastic. And as you can see, the lithosphere is where a lot of our plate tectonic movement occurs, and the boundary between the lithosphere and the asthenosphere occurs where the temperature reaches approximately 1280 degrees Celsius. So that's very, very high temperatures. And as you can see, the lithosphere here, it labels it as strong, whereas the asthenosphere is labeled as weak, and strong has to do with being rigid, and weak has to do with being plastic. Finally, our innermost layer of the Earth is its core, and it's composed primarily of iron alloy, which is mixed with small amounts of other elements, including nickel. Studies of seismic waves, seismic wave velocity changes have led us to distinguish among the outer core, which is here, and the inner core. The outer core is composed of a liquid iron alloy, and it's a liquid because the temperature of this is so great that it prevents the atoms of the iron alloy in the liquid core from solidifying and being locked into a solid framework. Even though the tremendous pressure that is exerted by the other layers on this liquid outer core, they will not solidify into solid because of the high temperatures. And because of its liquid nature, the outer core flows convectively, generating Earth's magnetic field. And so in contrast, the inner core is composed of a solid iron alloy. And this is solid because even though the temperature is hotter than the outer core, it reaches up to 4,700 degrees Celsius, the temperature that it is subjected to is insurmountable in comparison. So finally, in summary, we hope this video has helped with Standard 8.E5, in which 8th grade students will demonstrate an understanding of the processes that alter the structure of the Earth and the resources that provide for life on our planet. Specifically, the indicator that allows students to obtain and communicate information about the relative position, density, and composition of Earth's layers, including the crust, the mantle, and the core. And the content of this video is derived from Chapter 2 of Stephen Marshak's Earth, Portrait of a Planet, 4th edition, which is our textbook for Mr. William McGinnis's Geology 250 class. We hope that you learned a lot about the layers of the Earth today. Thank you very much.